Okay, so welcome to this next video in the playlist on the cardiovascular system. In this video, what we're going to do is we are going to look at nitric oxide synthesis. So we're going to look at firstly the three types of enzyme which synthesize nitric oxide, and then what we're going to do is we're actually going to look at the reaction that they are catalyzing and how we actually produce nitric oxide. Okay, so let's start with the three types of enzymes which produce nitric oxide, and they are all called nitric oxide synthases. Now, it's a bit of a misnomer because they're not actually synthase enzymes. Instead, they're oxidoreductases, but never mind. Nitric oxide synthases is what they were called originally, and we're stuck with that now. And it's quite a nice name. Okay, so they are nitric oxide synthases, and for short, they are abbreviated to NOS. Right, now, there are three forms of this enzyme, known as NOS1, so nitric oxide synthase 1, NOS2, and NOS3, so that's nice, sensible namings. However, the problem is that their old names are still very pervasive. These are the correct names for them. However, the old names which are still very pervasive are NOS1 is also referred to as NNOS, which stands for neuronal NOS. So this is equal to neuronal nitric oxide synthase, or neuronal NOS. Okay? NOS2 is often known as INOS, like so, which stands for inducible NOS. Okay, and then the final NOS is NOS3, which is often also called ENOS, which stands for endothelial NOS. Okay, right, now why are these old names, and which are still extremely pervasive in the literature, why are these old names not so good as these names here? These are the correct names, these are the incorrect ones. Well, the reason is that you can find NNOS in other places than just neurons. You can find ENOS in other places other than just endothelial cells. You can find inducible NOS constitutively expressed. However, these names are still very pervasive, and they do it to some extent have a truth in them. NNOS is present in neurons, ENOS is present in endothelial cells, INOS is upregulated in the inflammatory response, so in inflammatory cells such as macrophages, etc. So when NF-kappa B is activated in immune cells such as macrophages, it increases the expression of inducible NOS, and the macrophages starts secreting nitric oxide. Okay, but as I say, the names are misleading and make you believe that their expression is more simplified than it is. So NOS1, NOS2, NOS3 are the correct names for these enzymes now. Okay, now NOS1 and NOS2, NOS1 and NOS3 are activated by calcium calmodulin complexes. So these are activated by calcium calmodulin complexes. So that's an important part of their activation. So in order to activate ENOS, you need a calcium calmodulin complex to bind to it, and then it will begin nitric oxide synthesis. The same for NNOS or NOS1. NOS2, fun fact about NOS2, it's far more effective at producing nitric oxide than NOS1 and NOS3. The rate at which NOS2 can produce nitric oxide is around 1,000 times faster than the rate at which NOS1 and NOS3 can produce nitric oxide. So in inflammation, when INOS is expressed, these macrophages are simply chucking out nitric oxide because the INOS is an incredibly effective nitric oxide synthase enzyme. Okay, right, so that's all that I will say for now about the 3 different types of nitric oxide synthase. I now want to turn my attention to the actual reaction that they are catalyzing. And basically, the starting point, the substrate for the reaction which is going to produce nitric oxide is L-arginine. So that's a bit of an odd place to start. You might have thought, you'd be working with much smaller molecules than L-arginine, but in fact we're going to synthesize nitric oxide from L-arginine. So L-arginine is an amino acid, and I will draw out its structure here. So let's start with the basic amino acid structure. So here's the amino group of the alpha carbon, which is here. The alpha carbon also has a hydrogen coming off it. And here is the carboxylic acid group of that alpha carbon. Okay. Then, the R group of L-arginine looks like this. You have 3 methylene groups, so methylene, methylene, another methylene, okay, and then, after that 3rd methylene, you have a nitrogen atom here, with a single hydrogen off it, and then it's bound to another carbon. So this is the 5th entry in this chain of the alpha carbon, and then this carbon has an amino group coming off it, like so, and then it is double bonded to a nitrogen, which then has a hydrogen coming off it. Now that's the structure of L-arginine. Now, I just want to tell you a bit of terminology. This nitrogen here, this nitrogen that is double bonded to the carbon here, which I've circled now in blue, this has a funny old name. It's known as the guanidino nitrogen. So this is the guanidino nitrogen of arginine, of L-arginine, the guanidino nitrogen. Whoops. Okay. And it is the nitrogen that we are going to use in nitric oxide. So when we finally do get nitric oxide, it will be this nitrogen atom that has actually been put into our nitric oxide. Okay, right. So the step to produce nitric oxide has the reaction to produce nitric oxide has 2 steps. So the first step, what you're going to do is you're going to turn L-arginine into a molecule known as Ng-hydroxy L-arginine. So what you're going to do is you're going to bring in reduced NADP, so nicotinamide adenine dinucleotide phosphate. So you're going to bring in a molecule of reduced NADP, so that this notation here, NADPH, means reduced NADP. Now, it is confusing notation because reduced NADP actually has 2 protons, each with their electrons. So the hydrogen brings its electron, which I'll denote here, and you have 2 of them on reduced NADP. So, basically what's going to happen is this reduced NADP is going to provide 2 protons and 2 electrons to the reaction. So that's why I think it's confusing notation, because you might just think there's 1 hydrogen now because it's NADPH, but that just simply means reduced NADP, and reduced NADP has 2 protons and 2 electrons, so effectively 2 hydrogen atoms that are ready now to bind and interact. You're also going to put in, so you're putting this in, and it will come out as normal NADP or oxidized NADP, often denoted NADP plus, like that, to denote the oxidized state. So basically what you're putting in is 2 hydrogen atoms. You're putting in 2 protons and 2 electrons, okay, from the reduced NADP. In addition, you're going to put in an oxygen molecule, so 2 oxygen atoms double bonded together like that, so that's O2. Okay, now what you're going to get out is a molecule known as Ng, which means guanidino nitrogen, this nitrogen here, and then off that guanidino nitrogen you have a hydroxy group, so this is Ng, hydroxy, and then L-arginine. Okay, so you've got a hydroxyl group basically of the guanidino nitrogen. So that pretty much tells us exactly how to draw this molecule. So let's redraw out most of the L-arginine and then just replace that hydrogen there with a hydroxyl group. And that's Ng-hydroxy L-arginine. Okay, so here's the carboxylic acid group down here. Okay, a hydrogen off that alpha carbon there. And here are these 3 methylene groups here. And then that nitrogen here. Then a carbon off there. You've still got this amino group up here. And then you've got this guanidino nitrogen here with a hydroxyl group there. So that is Ng for guanidino nitrogen with a hydroxyl group of it, and then it's just L-arginine after that. Okay, now, the astute ones among you will have noticed that this doesn't make sense. We have stuck in 2 oxygen atoms and 2 hydrogen atoms, and what have we done? We've only added in an extra oxygen atom here. Well, what's going to happen to the rest of it is you're going to get an oxygen, the other oxygen from this oxygen molecule, bound to these 2 protons, basically. So, in essence, what you're going to do is you're going to cleave this oxygen molecule into 2 oxygen atoms. You're then going to bind one of the oxygen atoms to these 2 hydrogen atoms that you're putting in to create a water molecule, okay? Then you're going to take the other oxygen atom and you're going to stick it in the middle of this bond here. So you're going to break this bond, you'll then have a hydrogen atom, and this nitrogen atom will have a free electron. So let me just show this. Okay, so if this is the guanidino nitrogen here, still double bonded to that carbon, let's say we've temporarily cleaved this bond, each of those now has a single electron that is not in a bond. You'll then bring in the oxygen, it'll form a bond with the nitrogen, and it'll form a bond with the hydrogen. Okay, and then it will have 2 lone pairs of electrons as well, because oxygen has 6 electrons in its outer shell. So that's how it's all working out. That's how that first reaction happens. Okay, so at the moment you've got this Ng-hydroxy L-arginine. Now, let's turn our attention to the second reaction. Okay. Right, so in this next reaction, in fact we'll do this in the next video,